Okay, hello everybody. This is a course on dynamic treatment regime, DTR. And I'm going to use lecture note of the Professor Davidian. This is the chapter 2, summary of chapter 2, which is the base causal inference. Okay. So we have a so potential outcome concept is that we have potential outcomes under option A. So A could be control or treatment, right? And then we this is a potential outcome. And so we don't really observe both. We only observe one of the two, right? But we are interested in estimating the this quantity. So observational studies. So in order to estimate tau, we can use experiment. So that's one way. But sometimes we cannot really do experiment. In this case, we just use the observational studies and try to do some optimistic assumptions, make assumptions, and hope it works. So, so in the observational studies, the selection is so the individuals who receive the treatment may have different characteristics than those who receive. So basically, we receive treatment not randomly, right? It's basically based on physician's discretion or they own their choice. So we want to utilize auxiliary variable X to control the systematic differences. Okay, so if a variable relate to both treatment, I mean A, and the outcome variable. So A is a random variable, right? A is either 0 or 1. And also for each choice, we have a different counterfactual outcome. So if a variable relate to both A and outcome variable, it is called confounder. There could be several confounders of such as gender, race, age group, and education level, things like that. If suppose that the confounding variable is unknown, then we should take the confounders into the model, right, into account. So once the confounding variables are all included, then within the confounder, right, within the same confounder, the assignment of the treatment is essentially random. So that is basically the idea. So given the set of all confounders, the selection between the two doesn't really depends on y variable, the counterfactual y variable. So that is the strong assumption, but that's the assumption that we make. So we call no unmeasured confounder assumption. So basically, it means that the auxiliary variable X contains all confounders. So in general, there is no guarantee, right, that all confounders are included in X. So we assume that, right, X is large enough to contain all the confounding variables. The problem is that is an assumption that we cannot really verify from the sample. So it is impossible to verify this assumption. Okay. So to do anything with the observational data, we need three assumptions. One is a suitable assumption. So suitable assumption basically means that our observation is basically a function, this kind of function of the counterfactual. So this is a potential outcome, right? So potential outcome. So potential outcome is fixed. I mean, and fixed. It's kind of treated as fixed, and then you just choose, right? Either a equal 1 or a equal 0. You choose one of the two. So in that sense, they are fixed. That is often called the Stupa assumption. And then NUC assumption is this assumption 1, conditional independence assumption, or ignorability assumption. So ignorability of the selection mechanism. Positivity assumption is another assumption that we is hidden. We need in order to do anything with the observational data. So with these three assumptions, we have this result. We obtain the following result. So basically, this is, you can see that they are, so the data set has X and A and Y, right? So this is observed data. But Y star 1, Y star 0 is unobserved, right? And we only observe one of the two. So in that sense, if you just say the other compound, so Y star is missing or latent, whatever. So that's, in that sense, this is basically you have three observed variable, but using that you can actually compute the expectation of the unobserved variable. So this is you can call it identification. So you can identify this quantity from the observed data. So that is the identification condition. Okay. So this is the justification of 2. So Stupa leads, that's because Stupa is what? A times Y star 1 plus 1 minus A times Y star 0, right? And so then given A, so A is either 1 or 0, right? 1 or 0. So if A equal to 1, then you observe Y star 1. If A equal to 0, then you observe Y star 0. So basically, given that this Y star, I mean Y leads to Y star A, right? Given conditional on A equal to small a, you get this one. So that is the Stupa. So the implication of the Stupa. And you see, basically it's conditional independence. So basically your A and Y star is conditionally independent of a given X. So this can be moved. I mean, doesn't depend on. So as long as X is conditioned, you get a 3. So basically this one is equal to this, right? So that means we get this random variable, which is the observed data. So obtained from the observed data, and this is what you want to compute. And then this random, and then you want, so you have established these two. So we now have this equal, right? But we want the its marginal expectation or equal. So because this is equal almost everywhere, so this is a random variable, right? As a random variable, they are equal given X. So that means as long as the marginal property, so support, so two random variables have the same support, then having the two random variables equal leads to the same expectation. So that's basically about this result. Outcome regression. So this equation 2 basically implies that we can use outcome regression model. So implication of 2 is that we can use outcome regression. So tau is expectation Y star 1 minus expectation Y star 0. And so outcome, because of 2, right? Equation 2, we basically have this equality and we have this equality because of 2. Okay. So that means if we can somehow estimate this conditional expectation, so this is something you can compute uses x and a and y, right? So you use the observed data to compute the conditional expectation, and we call it q, and then it's a function of covariate, so x and a. Then basically tau is the expectation of q x1 and minus expectation of q x0. Okay. So so that is basically parameter that we are interested in estimating. But to apply this idea, we need to obtain this function q, right? So what you can do is use some statistical model to fit some kind of a regression model, right? So we use basically conditional expectation y given x and a. So this is a conditional expectation. So that's basically this one. So linear regression. Okay, right. So we basically we have a model, and model has this known function q with the unknown parameter beta. So beta is unknown, but suppose we know the q, so that is the model, right? And so the problem leads to estimating the unknown parameters. And estimating the unknown parameter is easy because this is a regression problem. So regression of y on x and a. So that, and y and x and a are all observed. So you can just apply the usual regression. And then once the model parameters are estimated, then we want to utilize this relationship to replace the expectation, the original expectation, by the sample mean, right? So sample mean. And so that is the tau hat. Okay, so that's basically the first approach using the outcome regression model. Second approach is called propensity score approach. So propensity score approach uses a model for the propensity score, right? Propensity score function. So like a logistic regression, right? So we can basically use that, and then if pi x is known, so pi x is what? Pi x is expectation probability of a equal to 1 given x. So then that means if you take the expectation of the mu hat 1 given, well, I think we will show that soon, so I don't have to show it here. So basically we use, so what is this? We use the a equal 1 cases, but only, so a is an indicator, remember a is an indicator, so we're gonna choose a equal 1 cases only, but divide by their probability, propensity probability. So that is a kind of a weighting, right? So that you can see that this is actually, so that's why you call the inverse propensity score weighting. So weighting means we have a 1 over pi as a weight, right? So that is the weight. And then the inverse means that we have an inverse. And the propensity score pi x is the propensity score. So that is why we call it inverse propensity score weighting. And this is estimation of mu zero. We have this. Okay. The same thing. This is the probability, the expectation, the probability over a equals 0 is 1 minus pi x. So the unbiasedness requires the same 3 conditions in addition to pi x known. So here's the proof. So so this equality we use Stuba, right? Because Stuba means y star. 1a plus y star 0, 1 minus a. So basically, if you put a, right, then this second term disappears. So only have this one. And then this is the second equality, is just the property of conditional expectation. And third one, you get this can be removed because of the NUC, right? And then that is NUC. And then from here to here, you get expectation. So that is the basically the propensity definition of pi x. And then if you need to cancel out the positivity, so it cannot be 0, right? So that's this one. Same, you can prove this. So using that, you can finally, so this is the estimator of the mu1. This is the estimator of mu0. So we can subtract. So that is the tau, which is this one. And IPW estimator is basically estimate pi by pi xi gamma hat. So gamma hat is gamma is the parameter for the propensity model. Okay, so it is based on the assumption that propensity model is correctly specified. So outcome model, outcome regression versus inverse probability weighted estimator both require 3 assumptions. And then outcome regression estimator uses the model assumptions on the outcome, while IPW estimator uses the model assumption on the propensity score. So these are different. They are these 3 are both common. Okay, and then we want doubly robust estimator in the sense that we want one of the 2 models are correct. As long as one of the 2 models are correct, then it is unbiased. So that is the basically idea of the doubly robust estimator. So 2 models, right? Model 1 outcome model, outcome regression model, model 2 propensity score model. So we want or, so I mean, we want this model or this model to be true, then the resulting estimator is unbiased, asymptotically unbiased. So that is the that property is called the doubly robust estimator. So to develop the estimator, the idea is to use the augmentation. So we start with the IPW estimator. So the IPW estimator is a weighted one, right? This one. So this is the IPW estimator. And then we use IPW estimator, and then this part is basically lambda augmentation. So that is mean 0. Why? Because the expectation of A, right? The expectation of A is equal to pi, conditional on X. So the expectation, so this guy has a 0 expectation. Under the model, under the assumption that pi is correct, right? So pi x gamma is correctly specified and gamma hat is consistent, converges to the true. So under this assumption, this is reasonable estimator. But notice that this hx is arbitrary. It doesn't matter. So we don't. So that means this is a class of estimator, in the sense that we choose different hx, right? If you choose different hx, then you can obtain different estimator, but they are all unbiased. Okay. So that is a nice problem. And so the question is then, what kind of hx should I choose in order to minimize the variance, right? So that is the basically the research question that originally considered by James Robbins and his colleagues, and then later by Chettis. Okay. So the second term, is essentially augmentation space. So so the solution to this kind of problem is that the optimal solution H star is this form. Okay. And so so H star is this form. So so then that means the numerator part is an outcome model, the denominator part is kind of a response model, right? I mean the propensity score. Okay, so I'm going to explain this a little bit soon, but let me just assume that this is acceptable. So we accept that this is optimal. Then how to really estimate H star from the sample? You need to use this because this one is QX1 by definition. This is QX0, right? And so you need to basically use the estimated parameter to obtain the numerator and then denominator. Okay, so then this guy, it'll be you plug in here to construct the final optimal estimator. Okay, and equation 5 can be understood from this one. So basically, you can consider optimal estimation separately. So for mu1, using the missing data technique, we know that this is the mean of y1. So basically, you can this is just a one hx essentially. But this kind of setup, the optimal one is a projection. I mean conditional expectation of this guy given x. But we need a equal. So actually, let me write to be more rigorous. So this one, it multiplied by a, you will get yi star 1. Okay, so the theory says that the projection, so the optimal choice is optimal H star x will be expectation of y1 star 1 given xi. So that is the basically the regression estimator. So but this guy is equal to this because this is expression using the potential outcome, while this one is using the observed data. The same way, you start with this. So for mu0, you can also construct this. So IPW minus augmentation, but the augmentation should be something like this. And then you can check that if you so what is this? Denominator 1 minus pi I and 1 minus ai minus 1. So minus, right? Minus plus pi I. So you get a cancellation. So basically you see here you have a ai minus pi I divided by pi I, right? So you have the numerator part are essentially the same, ai minus pi I. Here you have ai minus pi I, the same. So the only thing is you basically denominator pi I and multiply by, so you have this guy minus pi I and this guy minus 1 minus pi I. Basically, leads to this solution. Okay. That is the basically the idea. And now, once you obtain this solution, once you obtain this optimal H star and plug in, and then it turns out that you can write this way. So this is basically what we obtained using AIPW with the H star. Okay, so this one. So you this one. You have this. So this one is a H, right? Some sense, and you basically obtain H star. Then after some algebra, you get this form. So then basically this guy is a doubly robust estimator of the mu1, and this guy is a doubly robust estimator for mu0. And why? To understand why, let's use this estimator. So n, subscript n means that you just assume that you observe the potential outcome and compute the sample mean of them. And then basically if you write, then this is just the sample mean of yi star y1. And then the algebra basically, so this guy is this guy, right? And this guy is here, this guy. So then combine the two, you obtain this one. So the expectation of this guy, so if you take the expectation, this is actually not trivial, but you can do some Taylor expansion argument. So end of the day, this will converge it to its limit. And then expectation, if you take the expectation, the conditional expectation given x, right? Then if you think about the conditional expectation, these two are conditionally independent. And then basically either this guy, or so you can get conditional expectation of the first term given x times conditional expectation of the second term given x. Okay, and then conditional expectation of the y. By the way, why we have this one? This is because of the conditional independence assumption. I mean NUC, no unobserved confounder. So basically you have 1 over pi I minus 1 or y star 1 minus q x. So this guy is 0 if the outcome model is true. This guy is 0 if what? If a propensity score model is true. So either one of the true model is true, then they have a 0 expectation. So the product is equal to 0 if one of the two is equal to 0, right? So that is basically the idea. Okay. So discussion. Well, this is the kind of a class, right? And then using the semi-parametric projection idea, this is a fairly a straightforward problem actually, and you can use projection idea to obtain optimal estimator. But the projection is relatively easy if the missing has 2 levels. So that's the one of the result that I covered in the projection seminar. Okay, so that's all for now, for today. And I'm gonna next class I will cover chapter 3. Okay.